Good afternoon, all. I nearly said good morning, all. I have this habit of saying good morning all the time when a lecture starts, regardless of what time of day it is. I mean, most of the time it's morning, but starting in just a minute or so because I do want to start on time, but I thought, I can fire up the stream because there is somebody here. Yes? She's always trying to make the decision of whether or not to jump on my lap or not. So, see if she'll stick around. You get a particular look at chicken in just this term because it's winter, and so she's like much more sooky and wants a lot of attention, or just wants warmth of having a human around. So I think she's just gonna sit on the desk next to me here. So yeah. All right. So let's talk COMP1511. There you go. There you got her just hanging around in the corner there. Reese Chicken does sometimes sit on keyboards, so sometimes she likes the warmth of the keyboards and will like try to send messages to people and stuff like that. But for the moment, she's just sitting on my other desk here. I've got two desks, one there and one there. Okay. Back to work. Lecturer in charge over here, assistant lecturer right here. So I'm assuming that everyone can hear me now. Just make sure that people can hear what I'm saying, not just what Chicken is saying. Because I'm not sure that she will be able to deliver the content in a way that you will definitely you will definitely get everything you need out of COMP1511. Alright, just making sure my camera's okay and it's actually on me. Chicken is 9 years old, so she's I think technically a senior cat at the moment. Yeah. Shady, I love eating chicken, and it's all just part of it. Like, I love her and I love eating chicken. It all just comes together. Okay, let's go. So, Tuesday, I was giving you the starting points of everything. Just like how's the course going to run, and what are the super basics of just getting a program started in C. So I know between then and now, there's probably a lot of people who have had a tutorial between then and now and a lab, and hopefully that means that a lot of the class are now set up for computing from home and have done more than one C program, not just the really, really simple C program I had, but you've had a go at not just making a program but editing it as well and things like that. So I will be continuing with that and not just talking about editing programs, but also some of the other functionalities. So we're going to start to build up our kind of toolbox of possibilities we can use for things. There's a question, can we use VS Code for the labs? Yes, you can use VS Code for the labs. Just bear in mind that if you want to do things like auto testing, which you probably should be doing in the labs, like we have tests set up to see whether the labs are working for you or not. Where like each particular exercise has a set of tests that runs inputs and outputs and sees whether they work or not. Auto tests won't necessarily run inside VS Code's build process. You're probably going to still want to use a terminal. So you can use VS Code as an editor and then pop out to the terminal to run auto tests and run DCC and things like that. So I know people who definitely will use VS Code instead of gedit. The reason I'm teaching with gedit or gedit, I've never really figured out which way that's pronounced, and I swing back and forth, is that it has so little. Right, so gedit has so little stuff going on that there's a minimum amount of stuff that can confuse anyone. So that's why I tend to use that, as opposed to something like VS Code that has a whole lot of bells and whistles. and it has a lot of really advanced features that I'd prefer we don't get into yet. Because someone asked me, okay, what's this advanced feature and why is it there? I don't really have the lecture time to go through all that. So you can use it definitely, and it will work. I would use it mostly just as a text editor. Because what we're doing is we're trying to teach you from the basics, and one of the most important things we do when we're teaching is we try not to bamboozle people with too much information at once. So that's one of the reasons why I don't necessarily drop VS Code on people who have never programmed before. But if you've used it for other stuff, go for it. Yes, and someone's saying, yeah, we actually have instructions in the home computing section of the 1511 website about connecting to CSE via a system called SSH rather than VLab. By the way, if any of this is going over your head, don't worry, you can just use VLab. Like, VLab's fine. I'm going to use VLab exclusively for everything that I teach in the course, so that's going to be what I consider the baseline. VLab using gedit and DCC and nothing else. So if you don't want to learn all these other tools, you don't have to for the moment. In the future, when you go deeper into programming, you might learn these tools because they're interesting, and that's totally fine. And I will hint at which things are going to be handy. Someone's tapping me on the shoulder saying I should get into the actual lecture content now. All right. All right. People are asking about future comp courses. Some of the future computing courses are set up with exactly the same infrastructure that we have. 1521 and 2041, maybe? I think those ones are the ones that are going to be doing that. You can use VS Code for the weekly tests and the final exam. Just make sure your submissions are done via our Give system, and you run auto tests and things. It's also worth compiling with DCC rather than any of the standard build processes that are in VS Code. I think you can actually edit VS Code to use DCC, but again, that's a lot of extra work going into things. Okay, so I'm going to move on and talk about the actual lecture and what we're going to talk about today. So, what did we learn last lecture? I think if you're going through the notes from the slides, I think I had yesterday written there, because I've adapted from last term, and last term I think we had 2 lecture days in a row, but it's alright, I just edited some of the slides. Okay, so we talked about course admin. Hopefully everyone knows where they can find help, so whether you're on the course website looking for information there, the course forum looking for information there, and also just some ideas about how we're going to approach learning about programming. We had a really quick look at the history of computing, like really simple. I only talked about 3 people, right? There's obviously been a lot more people than that, a lot more time and a lot more development, all these big companies doing things. Like, a lot of us know about Apple and Microsoft, the current giants, but there have been some big companies in the past that have really pushed computing. So I glossed over a lot of the history of computing because I just wanted to get into how we actually do it. I'm sure, I actually don't know if UNSW has another course. That would be in the arts and sciences school. There would be something about the history of technology there somewhere. I don't know though, I've never actually looked it up. And we made one C program and we compiled it and ran it in VLab, which is running in Linux itself. So, oh, hey Shrey. Good. Shrey's in there to answer questions, which will be handy. So, what are we going to look at today? So, first hour, we are going to look at some of the ways. Remember yesterday I was talking about computer, if we're going to separate into 2 pieces. One's the thinking piece and the other's the remembering piece. So one thing remembers information and the other thing acts on that information in some way or another. So the processor, we're going to call it, also sometimes called the CPU, which is just central processing unit, which is why we call it a processor, is the thing that makes the decisions and runs the instructions, like the lines of code that we write. The memory in our computer, and I consider memory to be like anything in your computer that stores information. So here I'm just being like glossing over all the different levels of memory. So there's your hard disk drive, the actual RAM, they call it, the memory chips in the computer, and there's also memory called registers and cache that are in the physical CPU itself. All of that stuff I'm just going to consider the same for now. I'm not going to overcomplicate things if I can help it. And this is just storage of information. And we're going to look at that today, look at some of the ways we can store information and the ways that we can use it in C. The second hour, we're going to start looking at, sorry, we're going to do some maths as well. I mean, it's going to be pretty low-level maths, like pretty low-level high school maths, not even anything complicated. But we're going to look at how we can translate basic arithmetic into C. We will occasionally do maths in this course, but generally I'm not trying to get you to understand high-end maths or anything in this course. So if there is any maths, what we'll usually do is solve all the formulas for you and say, okay, here's the solved formula, now translate this into code. Because what we're thinking about from a computer science perspective when we're using maths is how do we make this run in code rather than do we need to spend the next 2 weeks with a whiteboard and some pens and paper trying to figure out how the theory of this mathematical equation works so that we can understand it. In computer science, we're often going to let the professional mathematicians do the hard work on things like what mathematical theories we should use, and then we do the hard work in transforming that mathematical theory into computer code. That's also glossing over a lot of what happens. A lot of computer scientists do the maths themselves and then translate into code. Some people will consider to be doing more engineering work where they'll let someone else do the maths and then they will just transform it into a running program. So we're going to look at some maths. It's not going to be super complicated. Second hour, we're going to look at conditionals. So we're going to look at questions and answers in code. And we're going to look at the ability that we have to decide on the fly what code we're going to run. So I said this was something that we're going to do. This is one of the most fundamental things that a computer program does. It's not just going to exactly follow the steps that we give it. Well, it is exactly following the steps, but we can give the computer the option to go one way or another based on the situation. And so we let the computer judge the situation that it sees for itself and then choose which of its code it's going to run. And we're going to do that in its most simplest form today using this thing called the if statement. Okay, brief recap of yesterday. Not yesterday. This is going to happen every Thursday. I'm going to say yesterday, meaning Tuesday, and I'm going to say good morning at the start of the lecture, even though it's 4 p.m. It's just a thing. I don't know why, but I've just lectured so much in the mornings that I consider the mornings. And it's like the day in between the lectures just doesn't exist for me. It's probably because they only thaw me out when they need me to deliver content and then put me back on ice in between. Yeah. Yes. Oh, someone was asking about Lab Zero. Yes, Lab Zero event tomorrow is at 4 p.m. There will be a stream that I think is going to be running on my stream, so it should be easy because it's the same. It's in the same place that you expect to see the lecture streams. CSCSOC has a Facebook event for it as well, and I think, Shrey, you can even correct me. You can tell me that they're probably running it over their Discord. I know they've done online events via their Discord before. We will send out a message to you, a course notice. I think Tom's put one together, but he hasn't sent it out yet. So that might go out sometime this afternoon or tomorrow. Lab Zero is an event where people just sort of learn how to get around the systems in CSE. So it's like how to log in, how to set up your stuff, how to get VLab going. Although for the moment we're getting VLab going for everyone. Like it was how to get VLab going when we're in person and people didn't necessarily need it. And things like that. So just sort of getting a familiarity with how studying in CSE works, and so I think it's quite valuable because it teaches all the stuff that I'm not necessarily going to teach, because I'm going to teach all the academic stuff. But this stuff is just like how to get around, who to talk to, and things like that. So I think it's quite useful. So yeah, Matthew Bryan said it much better than I did. It's an intro orientation. It's like that's much easier. Yes, Lab Zero will be accessible afterwards. So there's a series of exercises. They're more fun than exercises, but they show you how everything works here in CSE. So it's a super awesome service that the CSE Society is doing. Oh right, they might be running it over Blackboard Collaborate. Yeah. Yeah, and it's different from the COMP1511 labs. That's why it's called Lab Zero. It's not actually run by COMP1511, it's run outside of COMP1511. Except there's a lot of us who are in COMP1511 who will be going along to that thing to help people. Okay, brief recap of yesterday's code. Yes, I said it again. We have comments. So these double slashes here allow us to tell the compiler, don't read this. This is not important to you as a computer. You will not be running these lines, and so we can write in these lines messages for humans. We have our hash include. This one is a standard input-output library. It allows us to run certain functions that will write text to my terminal, and it will allow us to also read text from my terminal. So we're going to go going through all that kind of stuff today. Here is my main function. We're going to talk a lot more about what functions are later. Like, function is a keyword in C that's important for things. The main function is where the program will always start. So in here we have the actual lines of code between these curly brackets. Curly brackets are a way of saying, okay, this is a section of code that is all put together for a reason. And the computer will actually look at that code with curly brackets and say, okay, this is a chunk of code, and I will consider it like one single piece. So this piece of code is going to run first printf hello world /n. So double quotes here says that this is the stuff that's going to go to my terminal. So printf is something that came from the standard input-output library and allows us to send text to the terminal. And we saw that yesterday. I could print this text to the terminal. And we also looked at the /n. The /n is like pressing the enter key. So if I'm in my terminal and I send a /n to the terminal, if we had an invisible cursor that was moving along and typing out the letters HELLOWORLD along, it would then move that cursor down to the next line when it saw the new line. So the new line is like the enter key. Return 0 is me saying finish this program, and finish this program with a 0 saying that this program is working. I'm going to explain more about what we mean by zeros and this thing here called int today. Okay, so I said computers are made up of, theoretically, two parts. One part that thinks about things and carries out instructions, and another part that remembers things. So today we're going to think about the part that remembers things. So computer memory, and this is actually what it's like inside. If you were to be able to zoom in close enough into like the nanoscopic scale of the memory in our computer, it's nearly like a whole bank of switches, and all these switches can be switched on or off. And these are ones or zeros. So these are what we call bits in a computer. And each one of these bits can only have two possible values, a 0 or a 1. But if we have enough of these zeros and ones, we can then use this ones and zeros idea to encode or represent much larger values or much more complicated values. As an example, Tay's reminding me that we didn't have a lecture yesterday. Thanks, Tay. That's very nice of you. I will continue to say yesterday every Thursday when I'm referring to Tuesday. But hopefully by the end of the term, I'll get out of this habit. And then next term when I'm teaching this course again, the lectures will be one day apart, and then I will start saying earlier in the week instead, and then I'll get all messed up. Don't worry, it's just the first week. I'm still getting back into my flow. Okay. So the ones and zeros are what we call bits. And these are the most basic building block of all the information in the computer. We will often put these bits together into bunches of 8, and they're called bytes. You'll see this kind of these words for measurements of a lot of things in computers. So you may have seen bytes before, because anytime someone sells you a hard drive or even a smartphone and stuff like that, they will sell you a certain gigabytes version of it. So you buy a current smartphone and they go, okay, there's a 64 gigabyte version of this phone, and that means it can store 64 giga, I can't remember how many zeros that is, I think it's 9 zeros, of these collections of 8 bits. Confusingly, if you get something like an internet connection, they will often talk in megabits instead of megabytes. So it's actually a different thing. It's off by a scale of 8. So if I have a 10 megabit internet connection, that means I'm roughly just over 1 megabyte of information per second if I have 10 megabits per second. So the bits and bytes are actually different, and it's a little bit confusing when they go back and forth between them at a consumer level. But now you know. And as computer scientists, you'll be the people who kind of know what this really means as you get further into it. Okay, so we're going to be working with these chunks of memory. We're going to be working with them to store information. The other thing you may have heard of is 32-bit and 64-bit systems. When we're using computer memory, we'll use it in chunks, usually of 32-bit or 64-bit sizes. In most of the computers we're using nowadays, they're 64-bit, which means actually the smallest chunk of information we tend to use at a time is 64 bits. But we're going to show you how we're going to use different sizes of information as we go. That's a really complicated thing. I don't want to go too much into how memory is accessed and stuff. Yet. Later we will talk about it. Okay. I'm going to introduce the concept of a variable. A variable is our way of putting something in code that says to the computer, I want you to remember something. So we say to the computer, I want you to remember a value. I have a number, and I need you to keep track of that number. So I say, here's the number is 42. I want you to remember the number 42 for me. So in order for us to do that, we have to say to the computer, look, I have a number. It might change value later as we use the program, but I need you to hang on to it. And so it's called variable because it can change. So I may be able to give it a value to start with, but then I may give it a new value later. I might say, add 1 to this particular variable, and my computer will go, yeah, cool. I knew it was 42 before, now it's 43, right? That kind of thing. In C, we also have some really specific stuff going on here, and stuff that we're going to remember so that we can use things. So every variable has a certain number of bits, and those say exactly how much information a variable stores. So we don't have an unlimited amount of information for any particular variables, but we do usually have enough to use them. I'm going to talk about some of the details of that when we get to the end of this section. So I'm going to give you the basics, and I'm going to give you some more advanced stuff as we go along. So to keep things reasonably simple to begin with, we're going to start with 2 types of number variables. And so we're only going to be using numbers for the first couple of weeks of this course. We get a handle on that, learn about how to use variables and their different kinds of forms, and then we're going to have a big discussion here about int main and stuff. Don't worry about that line yet. If it confuses you, don't worry about it. If you've seen other programming before, you may recognize that kind of thing. We are going to go over that stuff later, but for the moment, I want that to be something that you don't worry about right now. We're going to do the basics and learn about all this other stuff first. We will learn what the int means soon, yeah. But here it is actually. Int means integer. So anyone who's working on maths at the moment or has done some basic maths courses will have seen the definition of an integer before. I'm going to define it again now. It's a whole number. So 0, 1, 2, 3, etc. So there's no halves, there's no fractions, there's no decimals or anything in an integer. Then we've got this thing called a double. The name's a little bit weird. There's a historic significance for the name, but a double is going to be a floating point number, which means that it's got digits in the same way that an integer would have digits, but it also has a point in it, and the point can be anywhere amongst those numbers. I've got slides on these, so I'm going to talk about the actual variables. Yes, I'll talk about the different types of variables. We're going to talk about how we use variables in general as well. So, naming our variables. I mentioned on Tuesday that half our coding is for people. So, sort of 50% of the time when we're writing code, we're putting effort into making sure the computer can understand it and the computer can run it. But the other 50% of our effort is made to make sure that we ourselves understand what we're doing and what it ought to do, how to change it, and things like that. And also, if someone else was going to work with me, so I had a team working with me on code, um, they would also understand what I'm doing. So a lot of what we're going to do with variables is just make sure that we're naming them correctly. So if we're not naming them correctly, it's really hard to understand what a program's doing. It's really easy to make mistakes with that program. So for example, if I'm working in a program, good variables would be words like answer or diameter. Like diameter, you already know what I'm going to use this for. It's like part of a circle, right? If I just used A and B for the answer and diameter, it's really easy for people to get confused as to what I actually mean by that. It's like, what was B again? It's like, B's the answer. No, B's not the answer. B's the diameter. It's like, well, if we just named it right, we wouldn't even have that question. We wouldn't confuse ourselves. So naming variables well is like proofing yourself against making mistakes in the future. And also means other people can read your code and it's easy to understand. Some conventions that we definitely use with variables is we will use lowercase letters to start variable names. So this is a convention. Some compilers will even call you up on it depending on what you try to start a variable name with. There are things that will cause definite issues. I think numbers, if you use a number to start a variable name, I think that DCC will actually not like that at all. If you use capital letters, DCC will allow it, but there are issues there because we have capitalized names for things that mean something other than variable names. So these are the kinds of conventions that we start to get into that allow us to always kind of code in a way that other people are going to understand. So if we train everyone with the same set of conventions, then we're all going to understand each other's code. This is kind of like if we're learning to speak another language, it's like, oh, you put a capital at the start of every sentence. You could technically still understand it if the capital wasn't there, but since we all do it, it makes more sense for us to continue doing it so we can understand what people are talking about. C is case sensitive. So something that I talk about sometimes, I don't know if anyone ever had an English teacher, although we have international students in the course this term, so a teacher for the language that you speak. And if you ever wrote things to them or spoke to them in a way that wasn't absolutely perfect grammar, then they would refuse to understand you. So this hilarious idea that your teacher is just like, I know exactly what you mean, but I refuse to accept it because it's not formatted correctly. Your computer is like that. It's just like that, except funnier because it never understood you. It will understand things only in the absolutely perfect sense. So these two words here, answer with a capital W in it and answer with no capital W, are completely different things to your computer. There is no way your computer will ever look at these two and say they are the same. It won't even really say that they're similar. It'll say these two are two completely different objects in my code. And when these are compiled, they won't even have these words there anymore. They'll be compiled into like encodings of something, and it will just be two numbers that are completely different. So just be careful with that. This is a mistake we come up with a lot of the time, especially the first letter of variables, where people accidentally put a capitals there because they're just thinking in a particular context, and then the computer just says, nope, I have no idea what you're talking about, right? So just be careful with that. C also has some words you can't use at all. So for example, we've seen the word return, we've seen the word int and double. These things are reserved for meanings, like the int is a variable type, so I can't use it as a variable name. DCC will probably tell you if you've tried to do something like this, and it shouldn't be done. There are two ways to use multiple words in a variable name, because sometimes we have variable names that are more than one word. So sometimes I can put an underscore between words, or I could put a capital letter at the start of each word in there, except for the first word, so this thing here. The terms people use for these is, this one's called snake case, because it's like a snake that pops up and goes down, and this is called camel case, because it's like a tall animal that has humps in it occasionally, right? So snake case and camel case, don't worry. That kind of stuff's definitely not going to be in the exam. However, generally, once we use either one of these two ways of splitting words, we use the same way all the way through our particular program. I show you both of these because, and we're going to show you both of these all through the course, because the computing world is split pretty 50-50. I don't know if it's exactly 50-50, but you could just pick a random company, work for them, and they're going to use one of these or the other. So it's good to know that you can switch back and forth between them without a huge problem either way. How are we doing? Alright, there's lots of people talking about... oh, there's a question about, is there a reason for grouping bits into 8? It's a weird thing, but it's actually based on the fact that if you have a bit, then everything's in a power of 2. So you have one bit can have 2 options. If you have 2 bits, the number of things that you can represent are 4. It's actually 2 to the power of 2, because each one can be 1s and 0s, and you alternate between the 2. If you have 3 bits, you have 2 to the power of 3 possible things you can create, which is 8. And so very early on in the way that we were building computers, we got to the point of 8-bit computers. And 8-bit computers were a thing that happened for a while, and around that time is when the byte, I'm not sure if I'm just entirely making this up, but I'm pretty sure this is how it worked, is around that time, that's when the byte appeared. And so 8 bits became a byte. And it just sort of stuck at that point. So there's a lot of the times where bytes are going to be used because there was a significant period in the development of computers where we always worked in sets of 8 bits. And that's kind of funny because nowadays we don't work in just sets of 8 bits anymore. We tend to work in larger chunks of bits. But nearly every time we work in chunks of bits, it's always a factor of 8. So in a moment, I'm going to show you the size of an integer and the size of a double. They're a whole number of bytes, both of those. So an integer has a certain number of bytes of memory associated with it, and a double has a certain number of bytes of memory associated with it. So if you were going to kind of zoom out from the computer a little bit, you could say that we only work in bytes, and you'd still get away with it. Because the smallest size object that we work with in C is usually an 8-bit object, so it's usually a byte. I say usually because there's all these other ways of doing it. Programming language is very powerful, very modifiable. You can do a whole bunch of really interesting stuff with them. So when I say we usually work this way, it's because there's also another way to break that rule if you want to. Oh, there you go. Shrey has found a thread about the history of bits and bytes, which hopefully will just prove me wrong and you'll get the real information there, because I was just sort of trying to remember it off the top of my head there, and I don't know everything. Heaven forbid. Your lecturer doesn't actually know everything, by the way. We're actually just normal humans who've learned this stuff well and have a good way of presenting it. But there's always going to be questions you ask me that I don't know the answer to, which is also often more fun. You can learn a lot by picking at the things I say and then trying to figure out what happens. So a lot of the time students will ask me questions and I'll say, you know what, I actually really don't know that, because it's been so long since I worked on learning these things that I don't remember what it's like to experiment with them. So I think you'll find a lot of cool stuff like that. All right, moving on to the integer. The integer is potentially the most fundamental variable type that C will use. C will use integers in the place of a whole bunch of other things, and this basic idea of storing a number in a variable is something that C uses for a whole bunch of other variables as well. So this will be funny when we get up to letters and characters and things like that, because they're actually stored as numbers also. Everything's nearly a number in a program. The integer is a whole number. So a whole number means it has values, but it has no fractions and no decimals. Most implementations of C, so most of the times that C is being used, the integer is 32 bits. In the system we're using DCC and Linux, the integer will be 32 bits. If we want to use an integer that's a different size from 32 bits, there are possibilities for that. We're not going to bother looking at them in this course. We're just going to use the basic integers. It's not super important for you to be able to know that there are other sizes of integers. They're there. When you learn the context for how use them or why you might use them, then you can get into it. But for the moment, 32 bits for each integer. This also happens to be 4 bytes, which goes exactly back to, who was it that asked the question? Damn it. I'm scrolling back up. Oh, it was Kate. Yeah, Kate Fumara was asking the question about, oh, Shrey's telling me I'm covering up some of the slide. Yeah, so this is it here. An integer is being 32 bits, which is also 4 bytes, right? 8 bits in a byte. So as I was saying before, the number of bits you have to represent something gives you 2 to the power of that number of bits, different possible values. We're not going to get too theoretical about this, we're just going to think about ints being able to store a number. But the thing that we do need to think about is, with a certain number of bits, I am limited to a certain number of possible numbers. So 2 to the 32 possible different values. So if we're going to have negatives and positives, we can do 2 to the 31 in either direction, because this is 2 to the 31 plus 2 to the 31 is 2 to the 32, because there's 2 parts of that, right? So if we go back to our maths and our powers and things like that, 2 to the 32 is 2 multiplied by 2 32 times, which gives us these numbers. I don't memorize these because I just consider them really, really big numbers that I am unlikely to hit the limit of unless I do. Unless I start multiplying things by a lot or adding things up together. So you've got to be careful if you're going to go up to these massive numbers. But with 2 to the 32 possible values, this is the way C usually works, so I have 2 to the 31 negative values, I have my 0, which is considered one of my positive values, and then I have 2 to the 31 minus 1 values higher than 0. So if you add together 2 to the 31 minus 1 plus 1 for the value of 0 plus the 2 to the 31 values that are negative, that adds up to exactly 2 to the 32 possible values. We don't really need to go into too much detail about how this works or anything like that, other than we know that an integer is a whole number, no fractions, just whole numbers, and it does have an upper and a lower limit. The upper and the lower limit are really, really high or really, really low, but you can hit them. It's pretty easy to write a program that's going to hit these limits. If I just take something that says multiplies 2 32 times, I'm going to hit these limits, right? So that's how we're going to do this. So the only thing you have to remember is that going over these limits is going to cause problems. I'll talk about that later. But otherwise, these are the numbers we're going to use. All right, a double is a floating point number. The naming's a little bit weird. It's called a double because it's double the size of a standard number. So the integer is going to be 32 bits. You can actually make a floating point number that's 32 bits, but use the double because the standard nowadays is to use 64 bits for these at least, because it maintains a certain level of precision in them. So floating point means there's a decimal point somewhere in the number. So if you look at these two numbers here, 10.567 or 105.67, the digits are exactly the same, 10567 on both of them, but the point floats. So I can put the decimal point anywhere I want in these digits with a floating point number, and that significantly changes what the value of that number is. Floating point numbers like this have certain limitations. I can't remember if the slide is next or later. In that they have a limitation on exactly what level of precision they can attain. Let me see if I didn't put it here. I'm going to put it later. I'm going to put it at the end. I'm going to talk about the details of doubles. But basically there's two types of numbers we can use. One which is the integer, is the whole numbers. And that works for times that we're counting things and stuff, and we're not counting fractions of things, or we're looking at how many times we perform an operation. That's also counting things. Whereas when we're storing mathematical values and things like that, we tend to use doubles. So we have two different variables. One of them is a 32-bit variable, so it uses less memory. Not that we have to worry about how much memory we're using at this point in time, and it stores whole numbers. And we have another variable that stores, I guess, fractional and decimal numbers. I shouldn't say decimal numbers, because decimal, all the numbers we're using are decimal numbers, but it stores numbers that have decimal points in them. Okay, so some code for actually using variables here. Oh, Tom's here. Hello. Tom's answering a whole bunch of questions about things. Yeah, cool. All right. Nice. Terry's noticed that it is a binary system. Yes, all of our computers are binary systems in that everything at the lowest level are bits, ones and zeros, and that's what a binary system is. So the numbering system that is using bits is called the binary numbering system. Okay, so code for how to run variables. So when we say to our computer, I want you to keep track of a number for me, I would have to do that by first saying, okay, here is me declaring that a variable should exist. So I say to my computer, this line of code says to you, I have a number, and it's a whole number, and it's worth 32 bits of information. So I can say all of that with just int. So me saying int is saying, I'm going to store one of these standard numbers, and I want it to be called answer. When I do this, my program will say, yeah, okay, cool, I gotcha. We have our memory, so the program has access to the computer's memory, and it says 32 bits of that memory are now reserved for this keyword answer that's in this program. So nothing else can do anything with those 32 bits of memory. This is being used to remember this particular thing that the user has asked for. If we want to, we can then do what's called initializing the variable, giving it its initial value. So its first value, if it's never had one before, we call it initializing. And this is using this equals here. So we're going to get into this a bit more later, that equals in code is not the same as equals in maths. So when I say equals in code here for answer, what I'm saying is take this value that I've given you. This value is 42, put it in this variable. So when my computer sees this, it says, yeah, okay, so previously this variable answer was 32 bits of memory somewhere in my computer. So there's all this memory, and there's a box of memory somewhere that has enough space in it to fit one variable, one integer variable, and I say put 42 in there. So it's like, yeah, cool. I'll go in there and I'll flick the ones and zeros until that thing means 42. Now we're not going to go into too much detail about exactly how we flicked those ones and zeros to make that equal to 42, but if you want to, you can look up different ways of doing binary encoding for numbers. We'll probably have a quick look at that in the labs, in the tutes next week at least, to give you an idea of how it works, but we're not going to go into super detail about how this works. If you do want to know how this works, there are other courses I think that will delve into more detail on this. I think some even of the first year computing courses, and there are some maths courses on things like discrete maths that are going to look at stuff like this. So this equals says, I've taken the number 42 and I want answer to now be that. And so it will go, yeah, I remember 42. And I'll remember 42 until you decide to do something different with it. And if we want to, we can give the variable a different value using the same type of code. So if I say answer now equals something else, then my computer's going to say 7. Good. I'll wipe the 42 and I'll rewrite 7 in the space where that memory is. And if you ask me what answer is later, then it will equal 7. So the way that we're running code inside our main here is we're going to go line by line from the start to the end. So at this point in this line, int answer doesn't have a value yet. It's just a space where we could put a number value in at some point. After I run this line here, the number 42 is put into that piece of memory. And so if there were other lines of code between these two, anything that wanted to use answer would see 42. And then we'd hit this line here, and the 42 would be overwritten by 7, and any lines of code after here, until we change it to something else, answer would equal 7. So we get this kind of thing where our program is kind of a timeline of things happening. If we want to, we can do a declaration of a variable and an initializing the initial first value of that variable together in one line of code. And we'll do this a lot, actually. It's very rare that we will declare a variable and not give it a value. I mean, we still can, It depends. Different situations will call for it. But in this state here, it's a little bit dangerous because we don't have a value for it. So if I started using answer between these two lines of code, I would often get an error, or I would get a value that I'm not expecting out of it, and things get a little weird. So if I do it this way, I can say, give me the memory for a variable, and since I'm declaring it by saying it's an integer, and here's the name of it, and this is my second variable here, I'm calling it answer2. It's probably not the best variable name, but since we have no purpose for this code yet, it's hard to say what it should or shouldn't be. This will give me another 32 bits of memory somewhere else in my computer, and I will give it the number 88. So the second we create it, we'll go through and we'll wipe whatever was there. There's probably nothing there to begin with, and then we'll put the numbers in so that it means 88. Okay, so we had a quick look yesterday at printing just text. So we could print out hello world. In your tutorials and labs this week, you're also going to be printing out more things than just hello world. We can draw ASCII art and do some cool stuff like that. But what we're going to do here is also think about what it means to print out the value of a variable. So when we're using our printf here, I'm introducing this new symbol here. This is %d. So %d allows me to print, and this is shorthand for a decimal integer. So this is allowing me to say, I would like a decimal integer to be printed out to the screen. And decimal integer is the same thing, basically, as this integer here that's a number 7. So what I'll do here is, in my string of text, in the same way that /n was a symbol that I was going to use to mean something else, the %d is a symbol to mean something else. %d says, I'm going to give you a variable, and I want the value of that variable to be put into the string of text that goes out onto the screen. And so if I said, I'm going to give you a variable, I then need to actually deliver the variable itself. So I'll put a comma after this, and I'll say, here is the variable itself. So the variable is this one, and you can see how it's the same name. If it's not the same name, it won't be able to find the variable. And so when it sees that name, it'll say what value is in that piece of memory that the variable is holding. It'll find the 7, and it'll replace this %d with a 7 before it sends it to the terminal. So, oh, that's an interesting question. I'm going to let you handle that one, Tom. Matthew Petrella is asking, if you declare a variable, does that mean you can access other programs' abandoned memory? Kind of. This is a huge can of worms. I'm going to let Tom answer that for you. But to a certain extent, all memory in the computer, especially if a computer's been running for, if you don't turn off your computer for a few weeks, chances are every piece of RAM has been used by another program at some point. Different programs at different levels of how well they've been made and things will abandon memory in different ways. Sometimes when something gives memory back to the system, it tries to clean it all up. However, that's not very efficient, can slow down your system, so sometimes it will just literally abandon it. So there is a possibility, this is like a really old school way to hack a computer. There used to be ways that you could actually look in the memory of the computer for stuff that had been there before, and then use that to actually hack into someone's computer. There's a really interesting story about someone who coded the snake game. Like the game where the snake just walks around and it tries to avoid hitting itself and then just walk in open space. And they did that with the 1s and 0s in memory. And when they were coding it, they accidentally left a gap in one of the walls. So the snake actually walked out of memory for the program and into just the open memory of the computer. So into other programs' memory, into the operating system's memory and stuff, and it just walked around, and it just walked everywhere it found 0s, and it would turn them into 1s, and it would keep walking. And so a lot of the time the computer just crashed when that happens, but at other times the most interesting that happened was this is a really old thing, because modern computers won't even let you do this, but in the olden days, it was like the 80s or the 90s, I think, the CD drive popped open on the computer. So this thing had managed to make it all the way to the code that governed the control of the CD drive and flicked over the switch from close the CD drive to open the CD drive and popped it open. So there are kind of ways to access memory in the computer that's there and that other things have been using and stuff like that. We're not going to go too deep into that stuff though, but funny little things can happen like that. Okay, so printing this out is saying find this variable, and so if this variable hasn't been declared previously, we're not going to be able to do it, but hopefully it has, and then we can take the number and we replace this %d with whatever value we found in this variable here. %d specific, because %d says decimal integer, so it's only going to work with our integers. If we want to do it with our floats, we use a different one called LF, which is this one here. Let me go back to the other one afterwards. So if we have an integer or a double, LF stands for long floating point number, which is a double. I apologize for all the naming. There's a lot of stuff that when we initially look at C, we just need to sort of memorize things, which is why we have an integer as an integer and a double as a floating point number instead of something, a name that sort of makes more sense, because historically these things sort of shifted over time, and we're looking at a particular viewpoint on history from C at the moment. So we just sort of have to use it, and then later on when we get deeper into these things, I can probably tell you more about the historical significance or the connotations of these, but I don't want to bamboozle everyone too much. So the %d will print out a number as an integer. So anytime we want an integer to be displayed on screen, we're going to use %d and then the integer itself, which is the diameter there. If we're using a double, which is a floating point number like this one that we're calling pi, if we want that to appear on screen as this floating point number, then we will use %lf as the symbol. So it's interesting because the symbol /n was just 2 characters. The symbol %d was also just 2 characters, but %lf is 3 characters, but it still is considered as just one symbol by our computer. So I should explain what's going on here with the with the multiple variables, which is my previous slide. My flow of conversation was going the other direction, so I thought I'd show you that slide first. So if I want to print 2 variables, I have one called first, which is 5, and one called second, which is 10. First is, and a certain symbol, and second is, and another symbol. So we're using the %d symbol twice now. The %d symbol simply says, I'm going to give you a variable, and I want you to print it to screen as a integer, as a decimal integer, so a base 10 integer. I'm not sure if everyone knows everything about bases of numbers. So our number system that we use most of the time is called base 10 because the digits go 0 through to 9, exactly 10 digits, and then once we go over 9, we need an extra digit to store more information. The reason we use a 10-based numbering system is because of these. Like, there's no logical reason why we would use a certain numbering system over another, except our numbering system started off with us counting stuff on our hands. So I can have 10 possible things by counting on my hands, and then I stop, and I'm going to need another set of hands. So I've got another person, and they've got 10 sets of things on their hands, and they can count. So it's like our whole kind of like massive towering capabilities of mathematics is based on the fact that we evolved from a monkey with 10 digits. So it's pretty funny, like that's just how we started out. But that's how we understand it well now, and we consider it as like this kind of universal thing that things should have 10 values for their digits before they move on to another digit. And then we look at computers, and computers in their infancy have only two values that they can store, a 0 or a 1. So underneath all of this decimal stuff is the computer saying, no, everything's in 1s and 0s. So my numbering system is binary. Your numbering system might be decimal, and you meaty fleshbags must count with your meaty fleshbag fingers, but the computer counts with its high-speed silicon fingers, and a high-speed silicon finger is just a 1 or a 0. So there's an interesting thing you get with those numbering systems. So %d is going to give us a base 10 number. So these numbers are in base 10, and the numbers we expect to read are in base 10. If I want to print out 2 of these in one line with a printf, I can have 2 symbols, and there's no limit here. It's not 2. You could put 15, 20 of these things in there. That'll still work, so long as each one of these has a variable that comes after it, and the ordering is important. So if I have 2 symbols, and then I have 2 variables, the first variable will always match the first symbol, second variable will match the second symbol. And if I have a third one here and another symbol, they would match as well. So the thing's going to go in order. It's going to come through this and say, oh, there's a %d. I will match that up with the first variable I've been given. And then here's a %d. I'll match it up with the second variable that I've been given. If I leave out one or more of these, this line of code won't work. If I leave out one or more of these, I'm pretty sure the line of code will still not work, because it'll say you've given me 2 variables, but I was only using one of them here. So all that stuff kind of is going to fit together like that. We can also read input into variables. So now I'm going to introduce something new, which is scanf. Scanf is the opposite of printf. So printf is going to send stuff to our terminal for us to be able to read. Scanf is our program saying, I need the human to type something into the terminal. When the human types something into the terminal, I'm going to put that into the program. So I've got an example here of reading an integer, where I can have an integer declared. So I've said to the computer, give me enough memory for an integer. And in this case, I actually didn't initialize it, because I was going to give it a value using scanf. So I could say to my user, please type in a number, and then I will do scanf. Scanf is going to pause my program. So usually my program is going to run line by line by line by line, and it's going to take a few milliseconds per line, or even less than that. So it's just blisteringly fast, goes through the whole thing and runs it all. But if it hits a scanf, it says, oh, I have to wait for these humans. These incredibly slow humans. Why can't they make several billion decisions a second like I can? What's wrong with them? Right. So we stop at this point and we say to the user, please type in a number, and we wait. And there we wait. Someone can type something in. We're going to do all of this later, by the way. In the second hour, I'm going to put all of this into a program. And scanf has the similar kind of format to printf, where it has the double quotes and it has one of these symbols. And this symbol says decimal integer. So I'm expecting my user to type in a decimal integer. We're not going to stuff around too much with what happens when the user types the wrong thing in. I want to teach you a lot more about programming in general before we can worry about error correction and stuff like that. So for the moment, we're just going to assume people do the right thing. What we have is an integer. We get our integer there, and then what we're saying is write the value of that integer into this variable. And a little subtlety here is we have this and here. This little ampersand symbol says there's this variable somewhere in our computer, and I'm giving you a way to access that variable. So this thing actually says there's a chunk of memory somewhere in my computer. Go find that chunk of memory that matches this name and then write this number in there. We're definitely going to look at this and symbol later. We're not going to look any further than that. If you want to, you can just sort of ignore it and go, yeah, we use the and symbol in the scanf, but I'll tell you the deeper connotations of it in about a month and a half, I think, maybe about halfway through the course. We're going to start looking at these things. We could do the same thing for doubles, where we can say LF. Sorry, I'm going to move my mouse cursor away so it doesn't open the menu. So LF there says I'm going to type in a double, and then I'm going to store that double in this variable here. So now we have the ability to print stuff to screen. We have the ability to print variables to screen. We also have the ability to read variables into our program. There's another thing that's interesting, is constants. So constants are like variables in that they have a value, but this value never changes. And so because the value doesn't change, we can't call it a variable anymore. So it's called a constant because it's one of these things that we expect to be a value that stays that way for the entire running of the program. So we're not going to have a number that changes, we're going to have a number that's just fixed. So we do this with this thing called hash define. So we did hash include before, and these are things that are actually outside of our main program. So they don't run like lines of code. So if I said int pi equals 3, oh no, this would be a double pi equals this, that would be me asking my program to assign me a piece of memory. So give me a piece of memory and put this value in there. Hash define does a different thing. Hash define says match up this value with these letters here. So I've got this thing here and this thing here, and it'll say every time in my program that I see pi, I will replace it with this number 3.14159, etc., etc. I know some people can recite pi up to like a really long number of digits. I think mine runs out somewhere around here, somewhere after about 6 or 7 digits. It is obviously a sign of how intelligent you are for how many digits of pi you can recite. It's not, but it's fun. It's not, but it's a fun thing. Okay, so hash define will say that this is a value and it will be unchanging. It will go through our entire program from start to finish and it will never change. So, for example, that makes sense for something like pi. Pi being a mathematical constant to use with circles, it is something that we will not change the value of, because if we change the value of pi, it would cause problems for any kind of maths we're doing with circles. So we will set it up and we'll just use it for the entire program. We also name these slightly differently. We name these with all capital letters, and naming it with all capital letters is really handy for us, because now when we're using it in our program, because it's in all capitals, we'll remember that it's something that can't change, because we know that our variables, the things that can change, always start with a lowercase letter. So you've got this back and forth, the constants are capitals and the variables are lowercase. So that way, if I'm just scanning someone's code, if I see them working with a number and it's lowercase, I know that we can change it if we want to. If I see them working with a number and it's it's represented by something with capital letters, I'll know that it's a constant that I'm not going to change. So these are some of the things we're going to put into programs. I'm going to show you all of this later, right? Because I'm just throwing a lot of information at you at the moment. As I said, we're going to be pretty theoretical in the lectures. We're going to do a lot of just sort of dense, just kind of throw stuff at you, but that'll give you time to practice it as we go along. Basic maths in C. We can do basic maths in C. It's not that hard. Some of these operations are going to look really familiar. There's a plus, a minus. There is multiplication. The multiplication is done with an asterisk, not an X. If I tried to do it with an X, my computer would think that that was a variable name or something like that, so we have a different symbol for it. Division is the slash. So it's like having a fraction, having one number over another, which is a division. So we have a slash. So some really basic maths like this. Oh, we can use brackets as well to get some operations to work before other operations. So simple maths here is I have some integers I've declared that have values. I have an integer that I've declared without a value, and then I assign it a value based on some maths. So x plus y multiplied by x, which means 5 plus 10, and because it's in brackets, this gets done first. So this is 15 times by 5 is 75, and so this will print out, my maths comes out to 75, and then the enter key to move it down to the next line. The %d will match with result, so it'll print out the result variable as it is after this line is finished. So line by line, it'll go through. We're not going to go too deep into maths other than that for the moment. So there are more details. Oh, did someone say const? Oh, I'm not even going to talk about it. Hands up about const. I've done a lot of C++. In C++, which is very well related to C, const has, I think, 3 different functions that it does depending on where you put it. And it's super scary and it does all this weird stuff, which is why I'm not going to it. So here, while we're learning basic C, our constants are going to be really, really obviously constants. They're going to be all caps, hash defined things. And we're not going to use the keyword const, which is a keyword that can do stuff in C, but it does different things if you put it in different places, and that's really not what we want right now. So for the moment, what I'm teaching you is everything that we do right now is understandable because it does what it's supposed to do wherever you put it. Yeah, const's super confusing. Later on, we are going to get to confusing things. Maybe about a month and a half in, when we start doing direct memory access stuff, there will be there'll be some confusing stuff there. But I want to work up to that, right? So give some time. Yeah. So it's pretty funny. It was just like we heard const and we just run away from it immediately. Yeah. Oh, Weiwei's asking a really interesting question. Does constant have the space to store? I think what you're asking is, does it actually use memory? When I declare an integer, it goes, okay, here's 32 bits of memory, here's some space on my computer, and I can store a number in that. What's really interesting about constants is they do not. So constants are really weird because what they actually do is they're part of our program, and they say that every time I see the person has written, say, the capitals pi in the program, I will literally go through the code and I will find all the times that the person has written pi, and I will erase it and replace it with that 3.14159 kind of thing. So it's actually nearly like saying a hash define it's not exactly, there's more subtlety to this, but it's nearly like saying here is a global text replacement within this code file. So that anytime someone uses that within this code file, it becomes this number value. So the hash defined constant never gets given a piece of memory to store its number. It actually just goes through the code and it says, okay, everywhere in the code that I see this, I should treat it like this other thing instead. So it's a really good question, because that one comes up a lot, and it's an interesting thing. Ningji Lee is asking, what does int actually mean? If I put int at the start of a line, it will say I am making a new integer. So if I put it at the start of a line, it's saying the next thing I write after this is going to be representing an integer. I'm not going to talk about what that means for int main. We will talk about that later. I don't want to confuse things too much. Just use that as it is for now. But when we're doing it for something like this, this says I would like an integer. I will follow this up with what the integer is called. So if I say I would like an integer, I get given 32 bits of memory, and this 32 bits of memory I will trust to be written in a way that I can read it again later as a number, as a whole number. So it won't have the same kind of information in it for a double. A double will have information on digits as well as where the floating point is in those digits. The integer won't use any of its bits to decide where the floating point is. Then I will give it a name and possibly a value, and the value will flick the bits, some of those 32 bits, and the name will say, okay, this is how we find this thing in the future. Whenever we use this X, it'll go back to that same piece of memory. So there's a lot of like the bits underneath that's happening there. I'm gonna let Trey and Tom answer a lot of questions in there. Okay, there's a bit more detail in here that I'm gonna go into. I'm only gonna go into this quickly because these are side effects of things that might be a bit weird. Okay, ints have what's called overflow and underflow. Overflow and underflow are if we go over the top level of the number of bits that the integer can hold, or we go under the bottom level. So we go past the maximum value or past the minimum value. What happens when we go off the end of it is like, let me go back here. If I go off the end here, so if I get to this maximum value and add 1, a really interesting thing happens here is it just goes to the other end of the scale and starts coming up here. If I go negative past this end of the scale, it goes to this end and then comes back across. So overflow and underflow are potentially really dangerous because they can change your number from a massive positive number to a massive negative number. A little bit of funny trivia here. There's an explosion in the 80s or 90s of a rocket called the Ariane 5. So this actually had an overflow or underflow problem where I don't know if it was an integer or something else, in the telemetry calculations for this rocket went off the end of an integer one way or the other. And so this rocket's going up there and it's supposed to be making these like minute calculations for keeping itself upright as it goes. But that number was so high or so low, I can't remember which, went off the scale and suddenly changed to a very different number. This rocket, partway through flight, tried to make like basically a 90-degree turn and it ripped itself apart. So a tiny little error with an integer like that caused, I don't know how many millions of dollars worth of damage, destroyed a rocket and its payload and everything. There were no people on it, so it was good. I mean, that's not like there haven't been other space disasters where people have been hurt or killed, unfortunately. So, things to watch out for occasionally if you are going to get values high enough or low enough to overflow. Ints also might not always be 32 bits. Some operating systems and compilers can deal with ints being different values. When we were looking at doubles, there is no infinite precision of a double. There is only 64 bits worth of precision. So we do have possible issues where certain numbers can't be encoded at the absolute level of accuracy that we would hope, or we would maybe want out of them. So anything with repeating digits, so a number like 1/3, if I do doubles and I divide 1 by 3, I'm going to get 0.333333, but I don't get 0.3 repeater the same way we would in maths, and I don't get a number that just keeps going potentially forever. I get a number that goes 64 bits worth of 3s and then just stops. So at the end where it stops, that's where our precision finishes and we're not entirely perfect. So if we've approximated a number and then we say multiply it by another number and then we divide it by another number and we do all this kind of calculations, all with numbers that are not necessarily perfect precision exact values, we could get more and more further away from the exact perfect representation of things. Not a huge issue. Again, this is why this is at the end of this section. Not a huge issue, but know that they're not perfect. Know that they're only as perfect as the computer has space to represent them, which is 64 bits worth in doubles. Another thing is division. We're definitely going to throw some of this stuff in the tutorials and labs because I know that this is important for people to do, is that division with variable types is going to result in certain variable types. So if I divide two numbers that are integers, the value that I'm going to get at the end will be an integer, which means that if I do try to divide 3 by 2, it will not give me back 1.5. Because 1.5 is not an integer. Integers can only be whole numbers, not floating point numbers, not fractions. So if I divide 3 by 2, my C program will look at that and say, well, two integers being divided will result in something that is another integer. And what it will do, and it's important to know this because anytime we do division, we're going to need to know this, whatever fraction it finds, it will ignore it completely. So 5 divided by 3 should give us 1 2/3. Wait. 5 divided by 3? Oh yeah, it's 1 2/3. So in our logical math brains that we're thinking, we think that that should round up to 2. But our computer will not round it up. It's not automatically going to round to the nearest number. It's simply going to say, you gave me something that has a decimal point and some stuff after it. I'm an integer. I will ignore everything from the decimal point afterwards. So I'll take the whole numbers that you've given me, and that's all I'll take. So 5 divided by 3 will result in 1. We do have another mathematical function that we are going to use a bit here and there, and it's called modulus. So if we are dividing two integers, and we did get a 1 here, we can at least find out what the remainder was. So 5 divided by 3 will be 1 with a remainder of 2. To find out that remainder, we can use this % symbol to do a modulus operation. So 5 mod 3, that's how we say it, we call it mod. We'll say if 5 was divided by 3, we don't care about what the result is. We just want to know what the remainder would be. The remainder is 2, because 3 goes into 5 once, leaving 2 left over, and that's what the result of the mod will be. So sometimes we only look at the mod result. Like, we don't need to know anything else, we only need to know the remainder. So these are some of the more complicated things that we'll get into with variables and stuff like that. So I'm going to go on break now. So we'll take 5 minutes. Yeah, maybe less than 5 minutes. I'll come back like 5:15. I'll just stand up for a second, have a drink and stuff. So in the break, I'll leave this slide up, I guess. Well, actually, no. I'll give you a picture of chicken because it's nice. We can make a program with a series of instructions. We can ask the program to store some information, or we can ask it to perform a task. And usually, these are all going to go top to bottom, like a computer program, like a top to bottom, like a computer program. That's not the right analogy. Something like a cooking recipe where you go, you do this, then you do this, then you do this, you know? And so that's what our computer programs are, series of instructions that happen one after the other. All right, take a break. I'll be back in, say, 3-4 minutes time. Alrighty, I'm back. Chicken's here as well, but she's sitting down there. She's actually on the. She's actually on. Sorry, I just went back to the be right back thing. She's actually sitting on her little throne there. It's this weird little cardboard thing that she likes scratching and then sitting on. Okay. Let's just continue because I have a lot of content that I want to go through today and talk about. So we'll think about questions as well. Yeah, Tom, we talked about Lab Zero earlier. And both Tom and Shrey are talking in chat about Lab Zero. Lab Zero is an event that the CSC Society will be running, which is like it's neither like an orientation event talking about all the different things that you can do with the labs and, well, not just the labs, but what it's like to study at CSE and all the little things that could help you just sort of navigate studying here. So it's pretty handy because it's got a lot of tips on how to work with things like VLab and stuff like that, and also who to talk to, information about people in the school and stuff like that. Am I? No, I'm not cutting off. That's fine. And yes, and Tom has already sent out a WebCMS notice. I haven't checked my email today to see if that notice has gone out, but yeah, so that's out there somewhere. There's a couple little. Oh yeah, I'm gonna let Tom and Shrey answer those little questions so I can get onto content in here. All right, so some more Linux operations. We now have. I'm adding on some things, and I did at least see some questions in the forums. People like, how do I remove something? And it's like, well, now I can actually tell you about that stuff. So before we were just making directories and stuff, and now I'm talking about copy, move, and remove, which is the same as delete for things. Where is it? There. Into my VLab here. So ls is a directory listing, so I can do this to say, okay, what's in my current directory? CD changes directory, so I'm going to type in COMP1511 for this directory here, and I'm going to ls in there, and there's my lecture 1. So the other day I had lecture 1, and so I'm going to make a new directory using make dir. Don't worry if you don't memorize all this stuff first go. This is the kind of thing that takes some time to memorize. You'll get there eventually with a bit of practice. I mean, honestly, I'm not an expert in running Linux. I've actually spent most of my career working with Windows as an operating system. So you'll notice that, like, I don't really share my screen that much, but even here, you'll notice that I'm running Windows at the moment there. But I've also learnt a lot about running Linux, and I've run Macs in the past. I think it's good if you want to be a computing professional to be able to run different operating systems and be at least literate in the other operating systems rather than completely lost, you know. So anyway, if I'm going to make a new directory for lecture 2, here I can do make dir. I'm even using the abbreviations as I speak. ls shows me both of these. So let's say, for example, yes, what is it? She's trying to tell me that I'm supposed to be saying something different right now. Anyway, if I wanted to, say, get rid of this lecture 2, or let's say I wanted to, let's do this with files instead. I'm going to go into lecture 2. ls shows me there's nothing in here. I'm going to create a new code file using gedit. I'm just going to call it codedemo.c. Here, some code not important. So this isn't necessarily code demo. I'm just going to save this so that this file has something. If I do an ls now, I have codedemo.c. In fact, I'm just going to close this gedit window because I don't need that. So if I wanted to make a copy of this, I could do cp codedemo.c. And so this says I'm going to copy from this file to another file. So I'll make another file called demo2.c. If I do a directory listing now, there are 2 files here, codedemo.c and demo2.c. They both have the same contents in them, so they both have that one comment that I put in there. But one's a copy of the other. So it's the same thing as like doing a copy in file operations and stuff like that. If I wanted to get rid of one of these, I can rm. rm is removal. It's not only Rat Monster, but anyway, it's BTS joke. Don't know if anyone gets that. If I wanted to remove one of these, let's say I didn't need the demo2.c, I can do rm demo2.c, and then if I do a ls to list these, now that file is gone. So I've deleted it. It's gone forever. Goodbye. Just be careful when you do that. I think people are explaining Lab Zero. Yeah, there you go. I was waiting to see if anyone knew Army. Yeah, yeah. The BTS Army is representing. Anyway, so I've deleted one file here using RM. So that's a couple of these. MV is really interesting. MV is move, where if I wanted to, I could move code demo to a different location. So I could say move code demo. I press tab then. Tab's an interesting thing that will... I'm just going to move my camera across because this is really funny. She was just tapping me on the shoulder. Move will allow me to change the location of a file. So I can do code demo.c, and then I can start using the dots to do different things. So if I say dot, I mean the folder that I'm in right now. If I say dot dot, it means go up one folder. So this is going to go from my lecture 2 folder. The dot dot will take me to the COMP1511 folder. If I do dot dot slash, that means I'm in that directory. So I can do this now. And if I do a listing here in lecture 2, it's not there anymore. So it's gone. But if I do cd dot dot, which will take me up one directory, so you can see I've gone out of lecture 2 into comp1511. I do a listing here and I go, oh, code demo.c is here. So it's actually moved to this location. RM is raster mouse as well. Okay, so here I am with code demo.c here, and I don't want it here, so I can remove it now. Let's say, for example, someone's asking in there, I want to remove a directory. So let's say my lecture 2 directory, which is currently empty, I want to remove that because I'm not going to use it. So I could say RM lecture 2, but it says, look, you can't remove a directory because a directory contains other things. So we can't just say delete a directory and expect everything inside it to be deleted. That's where we come up with this -r. And before I use this, I want to say to you, be super, super careful with this. Like if you're a little worried about how this might work, then don't use it. Get help from a tutor, go to a help session, something, and ask someone else about it. Because unless you know exactly how this is going to work, I would not touch it. RM-R is going to remove all the files that are inside a directory and then the directory itself. So think about that really carefully. If I say this is going to remove all the files in a directory and then the directory itself, if I was to say something like this, I would be in a whole bunch of trouble, right? So just be super careful, yeah? So I've seen people do this kind of thing before, and then you can lose a lot of time trying to find backups and restore them and things like that. So we're going to be really careful with this, and we're only going to do RM-R if we really, really know we don't want something. So if I did this lecture 01, that'd be really bad because I've got files in there that I was teaching you with. But I do it with lecture 02, that's okay because I know that for the moment that directory is empty and I haven't started working on it. So RM lecture 02 is fine. If I look in here, I'm back to where I was before I did any of this stuff. All my files have been moved around and then deleted, and I've deleted the directory that I made. So here is just some more operations you can learn about how to do things in Linux. It's not that much different from doing stuff in Windows or OS X. The operations are the same. It's just the fact that we're typing them in that's different. So it's good to get a handle on a command line interface like this because there's a lot of stuff that we might do in a commercial setting where we wouldn't build a full, nice user interface for stuff. It would just be like, no, we're just going to run this code because this is what we're doing. So I'm going to go back to making my lecture 02 directory, and I'm going to change directory into lecture 02, so this is the direction I'm going to work in for the next half hour worth of this lecture. Okay, back to some theory. What's happening there? Oh, Shrey and Tom were explaining removing things and stuff like that. Michael's asking What happens if we try to remove our own student directory? I don't think you're allowed to do that. I think the system says you don't have that much control over it. Okay, I'm just going to move where my face is for this slide. So, because I can't cover up my memes, sometimes we're going to let our computer make its own decisions. So if we're going to let the computer make our own decisions, it needs to be able to look at a situation and decide what decision it's going to make. So before, with our code, we're running line by line, right? Just literally line by line. And it goes from top to bottom and it runs it all. If statements, the if and else statements, and I'm going to show you in a second, give us the capability to decide whether or not we're going to run parts of our code. So it's nearly like a branching thing. It's like, if something, then we do something, but otherwise we don't do it. We go off somewhere else. So the if statement looks a little bit like this. I always like to think of if statements as questions and answers. So the first thing we do is ask a question, and depending on the answer for that question, we will run some code or we will not run some code. So the if statement looks like this. We have the keyword if. This is another reserved keyword. You cannot name a variable if. That would cause problems. Your computer will say, I don't get what you mean. If is my word. You don't get to use if for your things. So we have if. We have some brackets. Inside the brackets is an expression. I'm not going to tell you exactly what that is because I've got the next couple of slides are going to talk about that. The expression will be deemed to be true, and I'm putting these in quotes because we don't have true false in C. We've only got numbers. We're like a raw programming language, just numbers. If it is not 0, it's considered to be true. If it's 0, it's considered to be false. So we get a kind of an if here that says if this thing is not 0, so if it is true, then we've got these curly brackets, and whatever's inside these curly brackets will run. If this thing is 0, then the if statement will say, I am not going to run any of the stuff in here. I'm going to skip to after this curly bracket and continue on with whatever code that you were going to do afterwards. We can add another condition to if statements that says, if this thing was false, instead do this thing. So now, instead of us saying, do this thing or skip over it, this says do exactly one of these two things. So we either do what's in the if the expression was true. If the expression was false, we do what's in the else. So we're always going to run one of these two in an if-else statement, and it's going to be based on this question here, this expression. So what's inside these curly brackets is just lines of code. It's the same as the lines of code that we would put in our main. We can do the same kinds of things. But we need to think about what's inside this expression, because the expression is actually a fragment of code that works in a particular way. So we need the expression to give us an answer that we can read so that we can decide between these things. Oh, sorry, I forgot. I had another slide here. I was going to talk about chaining these things together. We can chain together ifs and elses to the point where we can do this else if thing. So we can do this, or if not that, if this, then we run this, else we run this. So one of these three things will run in this case. So if it's true, the first thing will run. Someone's interrupting me. I know. It's her dinner time. We don't usually lecture through her dinner time like this. Okay, so if expression 1 is true, then we run this. If expression 1 was false, then we come down to this else, and we test expression 2. So this will run. If expression 1 was false and expression 2 was true, then we run what's in here. Otherwise, if this fails, then this fails, we come down to this one, and we'll run if both of those are false. So if we want to, we can chain together all of these different possibilities and say we're going to run exactly one of these possibilities based on all these questions that we ask. And it can get really, really complex if we want it to. Yes, you're hungry. You're going to get used to this, because every Thursday she's going to be here complaining about food for the final half hour of the lectures. Or maybe I'll feed her Feed her, like, oh, we can have a bonus lecture where I feed chicken and just get to watch chicken getting fed. Okay, so this structure allows me to decide to run only certain parts of my code, which is really cool because now we're giving the computer the ability to kind of look at its surroundings, make a decision, and pick which part of the program to run. Now we need to think about what's in the expression, because in order to decide what to do, we need to ask the right question. And one of the most common things that we're going to do with these is use these mathematical operators called relational operators. Relational operators allow us to decide between things. Chicken mukbang. Okay, so we've got some of these you're going to know, because we've got less than and greater than, where we simply can put two numbers on either side of this thing. Less than or equal to, greater than or equal to. These are things that you know in maths. You just need to know what exactly the format is of typing these things in with characters. So less than or equal to has to be a less than and an equals to symbol. The one that always catches everyone is the double equals. We can't use a single equals in an if statement because we've already used a single equals to mean something else. Single equals says I'm putting a number into a variable. If I'm putting a number into a variable, then that's not asking a question about these things, that's performing an operation. So because we've already used the single equals, we use this double equals to ask a question about two variables and say, are these the same or not? So if I have two integer variables that are different named variables, but they have the same value, this equals will become true. And we also have a not equals to say the things on either side are not the same. Every single one of these things, if I put values on either side of it, so values or variables that have values in them, they will give me a 0 if this thing is not true, or a 1 if this thing is true. We then also have these things called logical operators, which are ways that we can work with zeros and ones. So we can chain together multiple questions and say, if... I know you're hungry. I know. She's so angry. The and says if both questions, these are things we can put in between questions. So if both questions are true, then the and will be true. But if either of the questions is false, then the and will be false. The or, which is here, 2 bars, will be true if either side is true, or will be false if both sides of this thing are false. Anyone, I'm not sure if there's anyone here doing electronics or any of the electrical engineerings and stuff like that. These things are gates. Electronic gates are things that take 2 sets of voltage in, and then they either pump out voltage only if the and or is true. We can also use the exclamation mark not to say no matter what the expression was, we're going to flip it between true or false. And I've got a table here that shows you a bunch of these examples of this stuff working. So I have a simple expression here, 5 is less than 10. 5 is less than 10 is something numerically that we can understand is true, because 5 is a number that's less than 10, so the result is 1. I can ask one of my new things, like 8 not equals to 8. So me asking whether the same number is not equal to itself is going to come up as false, because 8 is equal to 8. I can test my less than or equal to here. Is 12 less than or equal to 12? Well, because they're the same number, then 12 is less than or equal to 12 because it's equal to 12. So that's true. Adding in my logical operators. An and here says this entire statement will get a 0 or a 1 based on the results of both sides. So let's look at both sides and see what they are. 7 less than 15. 7 is less than 15, so this side is true. 8 greater than or equal to 15. 8 is not greater than or equal to 15, so this side is false. The and said I wanted both sides to be true if I was going to be true, but only one side is true, so the result is 0, is false. The or says I only need one side of this thing to be true. So 7 less than 15 is true. It doesn't even need to look at this side. In fact, in code, it will usually just go left to right. And if it can solve everything by going left to right, it won't bother looking at the others. So it's actually going to look at this side and say 7 less than 15 is true. I have an OR. If I have an OR and one of the sides was true, then the whole lot becomes a 1 here. And then I'm chaining together multiple levels in this final example here. So there's an OR here, so it would go left to right. And because we have brackets, we're going to do what's inside the brackets first. So it's the same kind of thing with maths. 5 is less than 10 is true. If 5 is less than 10 is true and it's one side of an OR, then this whole thing becomes true, regardless of what was in this right-hand side. 6 greater than 13, so that would have been false. So true, false, the OR makes the entire thing true. And then I say not, so I take my true and I flip it, it becomes false. And that's what the result is. Yeah, and these are the kinds of things where we can go through in much deeper levels of complication in all of these things and get more stuff happening. We'll practice more on this stuff in tutorials and labs, and get you thinking about how you can ask the right questions to get answers so that you can run your statements and things like that. We are going to start a little bit more simply than this. So, got 20 minutes left, rolling up the sleeves. Oh, someone's asking if we're doing digital circuits. We're not going to be doing digital circuits. We're going to be doing programming, which, I mean, in a sense, are digital circuits, but not in the same level of like flow of whatchamacallit, flow of electricity through things. Okay, so we're going to create a program, and this is going to be doing stuff with rolling dice in our games of catacombs and large reptiles, because I don't want to get sued. Although I don't think you can actually get sued for saying Dungeons and Dragons, but you know, sometimes I like to say that just for the fun of it. So I don't know if anyone else here plays D&D. I actually haven't played D&D in years. I don't know if anyone's done their background research on me or anything, but I'm much more of a tabletop wargamer than a Dungeons and Dragons player, so I tend to do stuff with lots more miniatures than Dungeons and Dragons. I paint miniatures for fun. Anyway, so this is the program we're going to create. We're going to have a user roll 2 dice, and they're going to, with those dice, have some results on each die. They're going to tell our program what the results of those dice are. Our program is then going to take the die rolls, add them together, and check them against a target number that the program knows that the human doesn't know. So the human doesn't know whether they're going to succeed or not with their roll, but they're going to type in their roll, and then the computer is going to tell them whether this thing succeeded or not. And we're going to tell them if the total of dice was higher, equal, or low. We might not do equal, we might just do higher and lower for the moment. Gian Cornalo is saying that D&D might be old enough that the copyright... I think it may not have, because they keep refreshing it. So I think the original publication is, 40 years old. I don't even know if 40 years is enough. But since they keep releasing it every couple of years in a new form, they may still have a copyright on it. Anyway, that's not important for programming right now. Also, my face is covering up stuff again. I'm going to move that. Okay, so if I want a program that's going to do this dice rolling thing, what do I need to do? I need a certain set of ingredients to make this thing work. So I need a way to talk to our user. So I need a way to give information to our user, which is printf. I need to be able to get the numbers that the user is rolling, so I need scanf. And I need to be able to compare these numbers against a secret number. So to compare numbers, I need relational operators like greater than or less than. And I also need the secret number. The secret number could be a variable or could be a constant. We'll use a constant, I think, to make things interesting. So we have variables and constants. And we also want to run different code depending on whether the user rolled above or below the target. So we want ifs and elses and things. So this should tie in together everything that we've been working on so far. Well, everything we've learned about so far. So I've got some code here that I am not necessarily going to go through the slides of. I'm going to hop across here and I'm going to actually code it. So gedit I'm going to call this dice checker. And I'll do the and there so that I can continue using my terminal while I've got this dice checker. Dice checker lecture demo. Because I've got 18 minutes remaining in the tutorial. Say again. Uncover the slide. Was I... Hang on. There we go. I'm not sure which slide it was on at that point in time. But yeah, my face was probably covering things up again. Okay. Back here. Okay. Dice checker lecture demo. My name. Email address to contact me. What are we in? June 2020. Yes, chicken. Yes, you're hungry. I know. Okay, some of the stuff we're going to have in every program that we're making. I mean, this is the only one that this is so far. This is the first one I've written in front of you. But some stuff that we're going to be using that I know we're going to be using. Standard input output. So we're going to include the standard input output library here. A random mouse droid noise. I'm pretty sure that's chicken rather than a mouse droid. That's her right there in the corner. The other thing I'm going to need is a main. So for the moment, don't worry about this stuff. I am going to explain what all that stuff means later. For the moment, just use this same line all the time for starting the program. Okay, so at this point, if I was to compile this program, it would compile and run. I might actually just put a return 0 in here to mark the endpoint of this. I mean, I could just use the close bracket as the endpoint. It would do the same thing. But sometimes I like to be extra completionist with everything. Okay, this will compile and run. It will execute exactly nothing, but at least it will compile and run, so I know that everything that I write further into this is going to be like code that fits into a program that's ready to go. So I talked a bit about what our program will need, a way to talk to the user, a way to receive input, and stuff like that. So first thing to do would be comments. So this actually has much more information in comments. I'm not going to do them in front of you right now because I'm short on time and I don't 100% need it. Zenon Peng's asking if the return 0 is actually needed. It's not technically needed because if you don't have it, the program will still just end. And if it reaches the end, it'll think it ended correctly either way. Okay, so the next thing we're going to do is we're going to have a target number, and we might call that secret target like this. And we're going to do that with a hash define. So this is the way I was talking about using constants. Secret target 7. I could change the secret target to something else if I was going to remake this program or recompile this program if I wanted to. But for the moment, anytime I use secret target in my code here, it's going to be treated as a 7. So that's a nice way for me to say, this is the secret target, and anywhere that's in my code that I use the word secret target, it then can be a 7. The beauty of this also is that anytime I want to change the secret target, I only need to change this number here. I could have the secret target in here 8 different times, and if I'd use the number 7, I'd have to go through, find all the 7s and change them, make sure I didn't use 7 for anything else. It's just really annoying. Whereas using the secret target means that anywhere in my code that I've written secret target, it's always going to refer to the same number, and I'm not going to get any issues with that. Okay, so I've got my secret number there, and I've got my main function. So let's, actually don't need to set up these variables exactly like this, but let's read in one die roll to begin with. So what I like to do when I'm writing code is solve little parts of the problem in pieces. And solving things in pieces gives me a chance to test whether these individual pieces of my code works before I add other things to it. So I'm going to start with the first die, and I might actually put a comment here. Read in and store the value of the first die. So there's my die 1, and then I'm going to ask my user something. I'm going to say, please input the value of the first die. I'm putting a colon and a space there just to be nice to my user, so it's like, okay, I give them a bit of room, and then after that, that's where the cursor is going to be, so I can scanf. Scanf had a particular format saying, I want a decimal integer. This is a whole number. It's going to be a whole number because dice don't have fractions. So it's going to be, let's say if I'm just using simple, normal 6-sided dice, then it's going to be the numbers 1 through to 6 are the possibilities. I'm not limiting this yet to any particular values. I'm just saying that's what it's going to be. For me to put this into this variable die 1, I'm going to need to say find the location of die 1 and put it in there. So this code here should read in the value of this. And if I want to just test whether this is working or not, I could do this. Oh, no, let's just say first die is, and then I can do %d saying this is a number value that I'm going to get from a variable. Or it doesn't have to be a variable, it could just be an integer value. I could put the number 10 in here if I want to. That's a lie though, that's not what the first die is. The first die is whatever I put into the variable die 1. Okay, so this ties in some of the stuff that we were talking about earlier. And you note that I haven't solved the whole problem. I haven't done the whole adding up, testing against the target or anything like that, but this is a good way for me to start off by saying, can I check whether this bit of code is working? I'm going to talk a little bit about how I'm structuring this as well. So note that I press tab for these. This white space is here. We use this white space to say, here's an open bracket and a closed bracket. The open bracket and the closed bracket are on lines that start on the far left. Everything inside them is inside. This makes it much easier for us to read things because I can just scan up and down my text here and go, okay, all this stuff is inside these curly brackets. If I was to open up more curly brackets, and we will in a moment, they'll be indented one step further, and that way it's really easy to just visually see what you're doing. I've also left a line in between these things because I consider this to be one bit of functionality, the thing that reads it in and stores it in a variable. This is another different piece of functionality because this is my little thing to test whether that thing worked. So I actually like to put stuff into paragraphs. And this is really interesting, right? Because this is something we would consider to be like something for writing. And writing things so that people can understand them involves using paragraphs. And I'm going to do that with my code because, as I said before, a significant amount of what I do in code is for human understanding. So the paragraphs allow humans to understand my code more easily. Okay, pressing Control S now to save this. ls here should show me dice checker. I also, you know, we're talking about RM before. This is a way to help out with that. gedit automatically saves more than one file, so it has this little tilde on the end of my dice checker here, which is a backup. So if I accidentally delete this file, I'll still have a backup at some point that I can recover if I need. So that's just a little safety measure that gedit does. Okay, I'm going to compile this. Earlier in the week we were talking about compilation using DCC. DCC requires a C code file to compile. So dicechecker.c is the file. And then I'm going to have an output file for this, and I'm going to call it the same thing, dicechecker for the moment. Press enter. If it doesn't tell me anything, it means it has accepted my code and then it has done what I asked it to do. You'll note that all of these commands, they'll only say something like this if something is wrong. If everything's going right, it just does it. So, Here we have a directory listing saying there is now a green one here called dice checker. So let's run this. Dice checker. Please input the value of the first die. So I'm going to input the value of the first die. I've got some dice here. I'm going to roll it. It's 5. Press enter. First die is 5. Okay, good. So this is the point where we say, I'm just going to grab a couple of dice here. I've got this. A friend of mine made these for me. They're made out of like, she molded them out of resin and stuff, which is really nice. Anyway, so I've got some dice there to roll for the next few things. At least I know that this part of the program is working. It's reading in the number I've given it, and it's able to output it again. So that's working. I probably don't need this line anymore. I was just using that as a test, so I'm just going to get rid of that. But I am going to now read in and store the value of the second die. So this is die 2. I'm going to do a slightly dodgy thing here and just use the code that I wrote before, but knowing that I need to edit it a little to make it work. So please input the value of the second die, die 2, and now this time we can't scanf into die 1, that would be really bad. We would overwrite the value that was in die 1. So we're going to do die 2 instead. Now, if we want to test that both of these things work, I could do another test. Printf. Oh, note this is another way that I do coding a lot of the time is I will complete a statement before filling it out. So every time I open a bracket, I'll usually close it immediately and then go back to the space in between them and type stuff. It's a little safety measure that I have. It's like, it's making sure that all my code is complete before it has all its details. Because otherwise, there's a chance I'll forget to close the brackets and then like you get a whole lot of errors in your code. So, printf here, and I can say total of the dice roll is, and %d. I'll show you something cool. This doesn't just have to be a variable, and it doesn't just have to be a number. Oh, Peter's saying, does the order not matter after the DCC? It doesn't. You can put the file one way and then the -o elsewhere. Those things can be at any point in the command. Okay, so the total of dice roll is this, and what I can do here is die 1 plus die 2. So instead of it being a single variable, it's an expression that ends up being a number value which will be able to be put in here. So I'm going to save this, and we're going to see whether that worked. So I'm pressing up and down arrows here to go through my previous commands. I will do this a lot when I'm going to recompile and rerun my program. So DCC, dice checker, so it's got my whole compilation command in here so I can rerun it. So that makes my code, and then I can run the code again, and I'm going to roll 2 dice. Okay, first die was a 2. Second die was a 4. Total of the dice roll is 6. I probably should put a new line on the end of this because this is a bit messy now. But I may not use that line again. Actually, you know what? I might leave that line in there because that might be useful to whoever's using this program. Alright, I'm going to let Shay answer those questions there. It's easier while I keep going with the code. Because officially I have 4 minutes left, so I do want to write more code than this. Alright, so we've got some variables, we're scanning in, and we can have a total. We can actually put this total in a variable as well. We're probably going to want a total variable, because we're going to be checking this total variable against other things. So we're going to be testing it against the secret target. So instead of just doing die 1 and die 2 here, I'm going to make a new variable, total, and I'm going to initialize it with die 1 plus die 2. So I could initialize before with a value, this mathematical expression of these two variables turns out to be a value. So this is like saying a number is the initialization of this, and this number is made up of these variables. So there's my total there. So I'm just sort of expanding all of the basics that I showed you earlier on in the lecture. So I have a total, which is adding up the two numbers that I read in. So die 1 was read in with this first scanf, die 2 with this second scanf, which was the first die, second die. Total adds them both up, and then we can there print out the total. So now I want to check the total against the secret number. And this is where I have my first if statement. So if, again, note the way that I write brackets. What I'm going to do is just press enter a bit here so that the code's in the middle of the screen. It's just easier to read. Let's actually no, I'm going to let Shrey answer the questions there. Yeah. Okay. So note that I've I've typed in all of my brackets, opened and closed, so that they're... Can you see this? She's patting me. This is like the I want food bit. You'll get your food soon. Okay. So, I have a question and an answer. So the question I want to know is, did the person roll a number with those two dice that was high enough to equal or beat the secret target? So what am I looking at? I'm looking at the total number. Oops. The total number of the dice. Was the total number of the dice greater than the secret target? I might actually do greater than or equal to. So let's say that they succeed even if they meet the secret target. So secret target. I've got some autocomplete here, so if I press enter when that thing pops up, your gedits, if you've run 1511 setup, should have this. So I can just use this thing that can see some of the other words I've typed and say, did you want to type this same word again? It's a little bit like typing on your phone, right? You can autocomplete things. So if the total is greater than or equal to the secret target, I'm going to put a comment in here for myself, because this allows me to remember what was happening here. So success means I could now print out success. I'm going to give you an exclamation mark. That's an extra thing for succeeding. So now, if I roll and it's above or equal to the secret number, I will get success. If it is not greater than or equal to the secret number, nothing happens and this program will just end. So let's have a look at this working. Okay, that one all went a bit weird. Sometimes my terminal gets a bit weird. If it does so, I can type in clear and it will just get rid of everything. It doesn't actually make it disappear, but it just makes my window look like there's nothing else in it, so it's a bit cleaner. So, compilation command again, and then the command to run the program. Please input the first die. Okay, I'm going to roll these two dice. I'm going to change that roll so that we can see the success. So the first one was a 4, and the second one was a 5. Total of the dice roll is 9. That is a success. Let's try running this again without the success to make sure that my if statement is working. So let's say a 1 and a 1. Snake eyes, you lose. Total of the dice roll is 2, and it did not say success. So maybe we want to say more than just success or not success. Sorry, success or nothing. So let's put an else statement in here. And I'm just going to put a comment here so that I can remember this. I'm going to call that failure. Printf. Oops. I mean, I kind of don't need those comments because I've got exactly the same word there, but you know, there's another exclamation mark for you. Failure. I can't remember how I did this in the slides. Did I say that? Oh, I said skill roll succeeded. Right. And skill roll failed. Okay. Back here. And, ooh, did I save that? Control S, just in case. Usually there'll be a star, an asterisk up here if I haven't saved it, so I think I did. Using my up and down arrow keys to find my previous compilation command, DCC dice checker. There. That checks that. And then I will run it. So now I should have a response if I succeed, and I should have a different response if I failed. So let's roll a dice. That's a 4 and a 5. That was the same as last time. 4 and a 5. Total of 9. Success. Let's run this again. Roll the dice. Hopefully it rolls lower this time. There you go. It's a 4 and a 2. Total of the dice roll is 6. Failure. Right? So now we have the die rolls are able to run different code depending on what numbers were input here. And if I run this code, I say success. Otherwise, I run that code, which says failure. So now we have a dice checking program. I'm going to upload this code to the course website. I'll probably put better comments in the top as well. I offer you a challenge. Can you put more if statements or more conditions in the if statement so that you don't just have the if and else, which is the success and failure? Can you put an else if in the middle there to detect whether a tie is different? So there's a success and then a tie and then a failure. Can you detect all three possibilities? So if someone matches the secret target exactly. Extra challenge for super bonus marks. These are bonus marks spelt with a C, not spelt with a K. It doesn't actually do anything for your course. It just impresses me. Can you do a double? Can you do something that if you roll the same number on both dice, it's reported as a critical, and then you can have critical successes and critical failures. So can you layer multiple if statements like that to get that working? So those are just challenges if you want to try this. If you're not up for the challenges, you can always just do lab exercises and stuff. They will build up your capability with if and else statements and stuff. That's for next week, by the way. That's not this week's labs, because heaps of people have already done their labs for this week. Okay, wrapping it up. We've covered a lot of content this week, but you will get time to practice it as well. Variables. We have seen that there are multiple types of variables, and each one has a certain number of bits that it uses in memory. We've talked about how to name variables, we've talked about how to give them values, and how to change their values, and how to use maths to change variables and things like that. We've also looked at conditions, so we've looked at if and else statements, and we've looked at asking questions using relational operators like greater than, less than, and things, and also chaining questions together using logical operators like and or and stuff like that. So that's it for today, and I'm only 5 minutes over time as opposed to Tuesday when I went a little bit more over time. I will put the code up in the lectures section on the website so you can go back over it if you need. We're going to wrap up the official part of the lecture here, but I'll stick around a little bit to answer some questions. I'm just going to take a really quick break and give this thing some food, and I'll be right back. And if anyone wants to ask me any questions afterwards, I'll stick around. Right, so I'll be right back. But if you don't have any questions, you can happily let the lecture go here. That's all the official content I was delivering today. All right, one sec. All right, I'm back. No more adorable interruptions for today, unfortunately. Um, can I live stream chicken eating? She doesn't eat in here. She eats out in the other room. Although I could probably feed her up on this desk here and show you in the future. But we'll see. Okay, so let me go through now and see what questions people are asking at the moment. If Shrey and Tom haven't covered, if anyone wants to ask any little questions, I will answer them. Yeah, people are already talking about those challenges that I put there. So if the total equals the secret number, you can have a critical success. I think that one was the tie. That's Alec is talking about there. And Matthew Deng is also talking about, okay, this might work, but we might have to look at the order of things. Where is it? There. Yeah. So in here somewhere is where the tie is going to be. And it really depends on which questions you've asked first, which ones are right next. But sometimes, if you just have kind of absolute exact questions, sometimes it doesn't matter what order they're in. I mean, obviously the final else is going to capture everything that you haven't asked about previously, so that does depend on order. Zen and Peng asks, can you have more than one else if? Yeah. So, let me just screw around with my code here. Should format this nicely. Copy that. Paste. Paste again. Total is equal to 1. Total is equal to 3. Total is equal to 5. I could do this if I want to. And I could say, look, particular things in the total have different meanings. So, wait, total 1's impossible. I rolled 2 dice. Anyway, whatever. You know, you can do this. So you can say if it's above this, it's a success. If it's below it, these all happen to be below the 7, although that would change if I changed this number. Each of these, I could say a particular thing happens to you. So this is like a very, very bad failure. This is a mild failure. This is less so, that kind of thing. Or these could even be ranges. So if it's greater than that, if it's less than or equal to 1, it's in here, that kind of thing. And this else may never get triggered if I do these in a particular way. But yeah, this can chain forever. You can get to the point where it gets really confusing to read it, but you still can if you want to. Alright, I'll put that back in the state that it was in before I started fiddling around with it. Eric was asking if this will be for labs next week. This particular example is not for the labs. This example is just in the lectures. Labs will be different questions, but they'll be using stuff like if else. Okay. Someone's asking, why is a simple hello world binary file so large? 17K on the laptop. Looked it up. GCC says it optimizes stuff. Why is there so much stuff? There's actually a whole bunch of overhead in a program, especially if you make a program the way we do in this, that ends up making it much bigger. So you'll find that your C file is much smaller than your program file in the beginning when we're making tiny programs. Later on it'll be different. It's because we are actually running a whole lot of code alongside your code with DCC. So DCC packages in a bunch of stuff so that when your program fails, it can tell you how it's failing. So we have it's nearly like your code's running, but something else is tracking your code while it runs, so that on the point of failure, it can report exactly what was happening at that point of failure. When we're making production code, that's meant to run at great speed. So, for example, like in computer games, we write code to go really fast. So usually when we've written code to go really fast and it fails, it doesn't tell you anything because it's like, dude, as if I had time to track all of your little numbers while I was trying to run at high speed. What we do is we sacrifice some of that and it makes the program bigger so that when something goes wrong, we can tell you about it. Because the purpose of our code is not to run at blisteringly high speeds, even though it kind of does. The purpose of our code is to make sure that you learn something from it while you're building it. So we have all these things in there that are checking how you're using memory, checking how you're using variables, and a bunch of other things. Oh, hello. You're back. Yes, come in. She's just standing by the door now after I've opened it, trying to decide whether she can come in or not. Yeah, so it's going to be bigger because there's actually a lot of stuff working in the background for it. So Shrey, I think you'll find that. So, for example, Shrey, there's stuff happening with whatchamacallit. GDB is there's actually a GDB instance running with it, so it'll tell people what the variable values were at the point of failure and things like that. Michael's asking if the dice roll thing is next week's Tute Lab. I think there is a dice question at some point, but I can't remember exactly what it is. Yes? Come on. Yeah. There. We're after the lecture now, so we can just hang out with Chicken. Okay, and people are looking at... Yeah, Eric. Can we make it if die 1 is equal to die 2 and die 1 is greater than 7 critical success? I think you kind of got it there. That's pretty much what a... Sorry, now the chickens are gone, you don't want to just like look at my crotch. That would be a bit weird. Yeah. Eric, I think your idea there of asking multiple questions and chaining them together with the logical operator is going to work really well. Roy is thinking about have a variable string and add parts for each criteria. Like add critical to the string if dice 1 is equal to dice 2 and add success if the sum exceeds the secret number. Yeah, that's a good way to think of it. We don't actually have variable strings at the moment. We only have print statements, but you could definitely do that. So check this out. This is where I think you're going with this thing, Roy. So I could do this here, but I could do this. Die 2. I'm giving away part of the challenge here, but you know, it's fun. Oops, learn to spell. So critical, and I don't put an end line or anything there on that. So what's going to happen is if that was that, then we'd print out critical. Otherwise, we wouldn't do anything, and we just move on to this. So this, if it's not critical, we'll just say success. If they're the same, it'll say critical before it says success or failure. So this line here could do that kind of thing where we're sort of piecing together our output bit by bit. I'm going to take that away, because when I give it to everyone, I don't want to put the challenge stuff in it, because it's just kind of like... Challenges are only for people who are like, I already know how to do if statements. I want to see what other stuff I can do. Eric, yeah, lecture challenge. It's just for fun. It's just me saying that if you want to go deeper in this, you can. Because, you know, like, if I do a code demo for you and I only spend 20 minutes, half an hour on it, it's not even as much code as you would do in a lab exercise. It's just to show the basic concepts working. That's why I throw the challenges in there to be like, all right, we could attach all of these things to each other and go further if we wanted to. Shayak is asking, is it a crime to initialize variables outside of somebody like int main? Yeah, I don't think that'll even work. Oh, maybe it will. Yeah, no, it will. I know C allows that technically. Those are things that are often called global variables, and if they exist outside of the curly brackets here, that means they exist everywhere in the program. Now, for the moment, our entire program is within the curly brackets anyway, but as we get more complex, we're going to have multiple different sections of curly brackets, and if you have one variable that manages to go between those sections of curly brackets, it's basically turns into this like Wild West, where this one variable, you have no idea who has control over it or how, which parts of the program, and anything can change it at a random time and stuff, and it gets super messy. So it's kind of like, yeah, technically it works, but it's so annoying to handle it, and it's so annoying to fix errors with it that we suggest you never do it, because it's not necessary for anything. There's always another way around the problem that is going to take you through paths that are safer. So I know that there are people who do it, and I know there are people who can handle it in a program, but it's kind of like if you had an expert race car driver and you took away their brake pedal so they couldn't brake, they can still probably do okay. Probably gonna kill someone though, but it's really super dangerous, but they could do okay just through sheer skill. And that's the similar situation here. Technically, if you're really, really good at programming, you could do stuff with those variables and they'd still be reasonably safe, but they would never be as safe as keeping things contained within curly brackets. So I don't know if that's a good enough answer to that question, but like that's how you would do it. Where was I? Is there any way to set secret value to some random value? Johannes is asking that. Yes, there is. No, I'm not going to talk about it yet because it takes a lot of effort to get there. I will tell you about it, but I'm not going to do it. So there is a whole set of these libraries. They're called the C standard library. The C standard library can do other things. One of those things is a random number generator. So yes, we can use a random number generator. So instead of doing a hash define here, we'd make a variable out of it. We would assign that variable a random number from the random number generator, and then we would test against that. I just said it then, and it sounds simple, but it's much more complicated than that. So you've got to get the library for random number generation. You've got to generate the random number. Then you've got to make that random number fit within a range of numbers that makes sense for the die roll. And for the moment, we were doing really simple die rolls because we were just using 6-sided dice. I could have been using 20-sided dice, especially if it's Dungeons and Dragons, should be mostly 20-sided dice. But, you know, if we don't know all of that stuff, our random number could be a few billion, and then we'll just never succeed. So there's a lot more stuff. We are going to talk a bit about random number generation later, but not yet, because we need to talk about importing libraries and stuff before we do that. And that's something that I don't want to talk about now, right? Because at the moment we're learning how to piece together structure of code that will, for the moment, just decide which code to run or not run. We're not going that deep yet. Shrey's asking about the global variables. Yeah, I think I've sort of covered that. They're a bit dangerous. Yeah, and Roy was reminding me that I couldn't get a total equal to 1 if I was adding 2 dice up. Yeah, I sort of noticed that, and I was like, that's alright, I'll keep going. Oh, Erica was like, just to confirm, lecture challenge. No, lecture challenge is just do it if you want to, if you're interested. If you want to like poke at it to learn a bit more, but it's not any kind of like, I'm not going to be expecting a submission or anything like that. Zenon's asking, DCC is just a UNSW thing, right? Someone said that Andrew Taylor wrote it himself. Yes. Andrew Taylor is one of the senior lecturers at the School of Computer Science Engineering. He, if you are continuing in computing, you will see him, I think, in 2041 subject. I can't remember if he's also taking 1521, the subject codes for the different subjects. Yes? Hello? Um, yeah, and so he actually designed a fair bit of this course. So he gave me this course partway through last year, and I've redesigned only parts of it. So a lot of the stuff is actually still his design for this course. Is that Eric and Jeffrey are having a conversation about which bit is correct or not? Oh, right, die one versus total. Yeah. Okay, I get it. Yeah, I get where you're going with that. Oh, and Shrey missed it as well. Sorry, I'm a bit behind on chat. I'm trying to be comprehensive and check everything there. I missed it too. I was like, yeah, it looks fine to me. What's the problem? Yeah, but it doesn't matter, Eric, because you had a good idea about what you were going to do with it. And I think that with a little bit of testing, you'd be like, oh, I get what's happening here, and then you'd fix it up. No big deal. Jeffrey's asking about specific miniature tabletop stuff. I do a lot of the Games Workshop stuff. I think the game that I have played the most in recent times is Warhammer Underworlds. I like it because it's a small game that you don't need to paint like hundreds and hundreds of miniatures to play, because you may or may not have worked this out, but university lecturers don't have spare time. Like, just the whole idea of having like a weekend to play games doesn't really exist to me. My weekend is spent preparing tutorials and labs for the next week so that I can release late on the weekend for the Monday tutes to have it. And then my weekdays are obviously spent either delivering lectures or preparing other content like tutorials, labs, weekly tests, and stuff like that. So I still love it, and I try to get together with friends. Well, haven't for months, obviously, because like most of us haven't been leaving our houses very much the last couple of months. But before that, we would meet up every fortnight and play some games together, and talk about painting miniatures and stuff like that. But yeah, I'm pretty much into like the whole Warhammer universe. But I also play another game called Infinity and lots of board games as well. Johanna said, which chicken? I'm not sure which chicken you're talking about. Programming is fun. Thank you, Jeffrey. I'm glad someone is enjoying themselves, which is good. Oh, Eric said, how do you comment out a large part of the code without doing the double line thing? And Jeffrey is saying, yeah, the comment with the stars. That's good. I don't need to answer that. Yes, I'll show you, though. If I want to comment out this whole section of code, there's the comment with a star. And look how all this has already gone blue. If I want to end the comment here, star, line, and so this line will run, but all of that stuff in there won't. So if I want to just chop out a huge chunk of code, I can do that. Often when people do these, they will do comments like this, and then you can type a whole section of text there. I might leave this like this when I upload it later. Shrey's reminding me that Andrew Taylor's taking 1521 and 2041. I think he's taking 2 subjects in one term, which is that's a lot of work. Like I haven't, yeah, but I mean like, okay. Funny note, Andrew Taylor taught me when I was a university student at UNSW. So he's been doing this a very long time. So he really knows what he's doing. Yeah, so I guess someone with that much experience, if they take 2 subjects at once, I guess they can do it. I don't, and I'm very scared of doing 2 subjects at once because I like to put a lot of time into a subject if I'm running it. Intentionally, Shrey. Yeah, right. Okay, so Haoming Wang is saying, why did the code scanf this ask me to input 2 numbers and ignore the 3rd number I put in? I'm not sure if the issue there is the lack of the and before the die 1, but I'm not sure. Haoming Humming, I think we'd have to look closer at your code. That's something I would definitely take to your tutor, show them the code, and say, okay, let's see what's happening here. Unfortunately, in this online lecture thing, I can't look at your computer. So usually in person, someone would just bring their computer to me and I'd have a look at it and see what was working and what wasn't. But I think that's something you want to talk to your tutor about this week. Next week we'll also have help sessions that you can go along to see. You could show them the code and they'll probably show you why that's happening. Mabel Yin is asking, can I move multiple files together in the terminal? Do I need to do it one by one? Let's have a quick look at this. So if I do an ls here, I've got 3 files in here. I'm just going to clear this for the moment. So there's my ls and there's my 3 files. So remember before I said there's a -r. The -r stands for recursive, which means it's going to go through and do multiple things. If I want to, I can move. Then if I want to do multiple files, I can do a star. If I do want to do multiple files with only certain names, I could do dice star, and it would move all files that start with dice and end in any other letters. But if I want to, I can just do star, and I'll do .. which would put them up 1 level. And so that's going to take all of these files here and move them into the COMP1511 directory. So if I do ls again, there shouldn't be anything left here now. It should have all moved. If I go cd ... COMP1511, and then do a directory listing for here, my dice checker files have all moved here. So if I want to move multiple things, I can use the star or parts of words and the stars to move only some things. So to move these things back, I don't necessarily want to do this. Because what this is going to do is it's going to try to move these 2 directories as well. But if I want to move only my dice checker files, then I can say dice checker. I mean, I could have just used dice, looking at these ones are spelt differently. Dice checker star is going to take all the files that start with dice checker and have any other letters afterwards. So it should be these 3 files, but it won't attempt to move lecture 1 or lecture 2 because I've said this is the file that I'm moving. Oh, I should actually do -r, saying I want to do multiple. Actually, I'm not sure if I need the -r at this point. Let's try without it. And I want to move these into my lecture 02 directory. I usually put a / at the end to say that it's going into that directory. Otherwise, it'll try to rename dice checker files to the file lecture 02. Okay. Directory listing, they should have disappeared. I go now into lecture 02 and have a look, and they've moved in there. Yeah, so just got to be a little bit careful about exactly how you're using these stars. Because if you do a star, actually looking at that, I didn't need the -r at all. So, yeah, it was this line, I think, here. Yeah, you can move multiple files just by having something that matches multiple files. Oh, Edison figured out the issue with Haoming Wang's question about the /n. So scanf will try to match the pattern that it sees there. So if you put the /n in there, then it's going to look for more than a number, which will do weird things. Yeah. Cherry Blossom's asking, is there an answer for the challenge at the course website? There's not necessarily. This challenge is not necessarily course content. It's just for anyone who's interested in seeing how much further they can push this code. So it's not something that I'm definitely marking or definitely needing you to do at all. So it's more just do it if you're interested. I mean, I probably could put something up there because we've actually half solved this already just in the discussion we had there. Mabel's asking, can I manually type the file names that I want to move? I think so. I think move can move multiple files at once. Let's test. Okay, move dice checker. Oh no, I can't. I can't do more than one file at a time if they're very specific files. Because If I was, I'll show you something funny. Move dice checker, and I don't move to another directory. I move it to the same directory it's in, and I give it a destination called dice check. Check this out. It was called dice checker before. I moved it from dice checker to dice check, and it has renamed the file from dice checker to dice check. So move doesn't just move things to different locations. It can move something to a different file name. It's a weird way of thinking about it, but the command mv can actually be used to rename things. I realize now that I had intended on talking about this in the lecture, but I got caught up in other things and I didn't talk about using mv to rename. So I'm glad you actually asked about that, Maybell, even if not everyone will see it. They will probably eventually learn this just by fiddling around with Linux. Scanf, Humming has a solution. Just found scanf will automatically change to next line, so we don't need to add the new line after the variable. Yeah, especially because scanf doesn't print out anything. Jeffrey's asking something about base 10 numbering systems for people with meat numbering systems, fleshy meat numbering, as opposed to high-powered silicon numbering zeros and ones. I think that was it. It's just base 10. The only reason we use base 10 is because we have 10 fingers, and our progression of mathematics came from us counting things on our fingers and then slowly codifying it into something more abstract and more calculated, I guess. Whereas computers do everything in binary because the most basic thing they have is a 0 or 1. Yep. People have move dice check ... / will it go into the markchi directory instead? Yes. So ... / is relative to where it is right now. So for example, if I do cd, so this is just an easy way of moving around, ... / goes up one level. So this is the level I'm at now, lecture 2. I go up one level, I end up in COMP1511. If I'm in COMP1511 and I was to type ... that would go up another level back to markchi. So let's press enter here, and I'm back in my home directory. Yeah. So you're right. We can do that to go up multiple directories at a time. And so yeah, you can move things around like that. Oh, and Shrey is saying if you use mv-n, it will not rename, so you can do things like that for moving things around without changing their names. Okay, I think we've covered everyone's questions there. It's actually quite funny with the live streaming, because this is it's like a simulation of what I would do in person, where in person I've got my 2 hours of delivery, and then I take a step outside the lecture and a couple of students will always follow me outside and we'll have a conversation about what's going on. The live stream is like a little bit more organic with that, because I just say that the lecture's over and then we hang out and stuff like that. Jed's asking cd ... equals cd ... / Yes. I think there might be some subtle differences there, but that should take you to the same place. I think the differences are when you're moving things. The / implies that you're moving into that directory, but I think you can move into a directory without the /. I can't remember why I do it, but I do it on instinct, even to remind myself that I'm going into a directory when I type that. But yeah, Jed, I think they're going to be exactly the same thing. All right, I'm going to wrap it up there. Thanks everyone for hanging out. Hope everyone enjoys their tute and lab this week. Remember that Lab 0 is happening tomorrow, so I'll be there for the stream in the afternoon. So there'll be a stream with me happening, and then there'll be this going into breakout rooms and stuff like that. So I think what we'll do with the stream is the same thing we did last time, where I go on a video call with a bunch of people from CSC SOC, and then I stream them all to YouTube so you can see it. But we'll put the stream link up and stuff like that sometime later today or tomorrow morning, and that should all be ready for you. So see you all. Well, whoever's coming tomorrow. Not everyone, I think, can definitely make it because it's not a scheduled thing, but if you can, it's good. If you can't make it, we will put up some information about how you can do Lab 0 on your own if you want to. Okay, see you later.